Okay, this lecture is on Chebychev polynomials. Chebychev polynomial of the first kind is defined recursively. We let t sub 0 be equal to the constant polynomial 1. We let t sub 1 be the linear polynomial x. And then we say that t sub n plus 1 is equal to 2x times tn minus 1 for any x greater than or equal to 1. On this page, what we've done is simply substituted in the formula. We've got our seed values here, and they enable us to calculate T2. We take T2 and T1, we roll it in again, and we can get T3, and we can take T2 and T3 and roll it in the recursive formula and get T4. What I want you to notice is, notice how all of the even ones with even subscripts have only even degrees in them. Okay, and the ones with odd subscripts only have odd degree terms in them. And notice, though, that all of my leading coefficients are powers of 2. Okay, 2 to the first power, 2 to the second power, 2 to the third power. You're going to want to remember that. Okay, so we have the theorem on Chebychev polynomials, which just to me kind of miraculously expresses our nth Chebychev polynomial as a formula in terms of trigonometric functions. Now, how cool is that? How do we prove it? Well, we do it by induction, and we have the two basis steps on it because we're going to be using our inductive formula. For n equals 0, we plug in the 0 to that formula, and it turns out 1, which is, t sub 0. For n equal 2, we substitute it in the formula, and the same thing happens. So basically, we get those for free. Now, let's have the assumption that this formula does hold, okay, for k between 0 and n, and let's see if we can use induction to show that it works for n plus 1. Okay, so first off, we have these formulas from trig that you should sort of remember. It allows us to boil down and give us this nice little formula here. Okay, and then we let theta be substituted cosine inverse of x. We roll that in, and it gives us this guy right here. But our induction step lets us substitute in our Chebychev polynomials right here, and well, there you go. It just all sort of falls out. Okay. So some useful facts that you can pick off from that formula is that since between x equals -1 and 1, it's just the Chebychev polynomial is just a cosine of something. Its absolute value is less than or equal to 1. We can put this cosine of j pi over n into our formula for the Chebychev polynomial, and it will spit out -1 to the j for us, right? And we can, again, by rolling in that formula, that this will get spit out as 0. Okay, so you can take a pencil and paper and this formula here and check all those consequences if you want to. Okay. This brings us to the theorem on monic polynomials. And a monic polynomial is just a polynomial where the leading coefficient is 1. Okay? So if you have a monic polynomial, this is saying that the maximum value of that monic polynomial on the interval between -1 and 1 is going to, the maximum of the absolute value is at least 2 to the 1 minus n. And you might think of this better as being 1 over 2 to the n minus 1. Okay, because it's going to be a small number. This maximum on this interval, it's going to be bigger than this small number, but it will be it gives us some idea of what it looks like. So let's start off proving this. Okay, we will try to get a contradiction. Suppose that the absolute value of p of x is less than 2 to the 1 minus n to get a contradiction. Okay. Now let's let q be defined as in terms of our Chebychev polynomial. We're going to multiply it by 2 to the -1 over n. Why are we doing this? We're doing this to turn it into, our q is going to be a monic polynomial. Okay. And let's let x of I be cosine of I pi over n. Okay. So note that q is a monic polynomial of degree n. Okay. Again, you said just what we noted when we were working through them, that all the leading coefficients were powers of 2. Well, this is just exactly the thing you need to multiply through to make this to make it a monic polynomial. And now we'll go through, consider -1 to the I times p of I. Okay, we don't know what this is other than it's monic, but okay, it's less than or equal to the absolute value of the thing. By to get a contradiction hypothesis, we know that this is true. All right, and we know that this is true from those formulas that we calculated about the Chebychev polynomial. Okay. So therefore, what can I do here? I could subtract this from both sides of this inequality, and it tells me that this is greater than 0. If I factor out the -1 to the ith power, and I, typo, that's never happened before, this is greater than 0. Okay, therefore, q minus p changes sign n plus 1 times on that interval. Therefore, there are at least n plus 1 roots in that interval. However, q minus p has at most n minus 1 as its degree because the leading terms cancel. Okay, therefore we have a contradiction. Beautiful algebra. All right, so how does this connect to interpolating polynomials? Because remember, we're talking about interpolating polynomials. Well, if f is a nice function, continuous with n plus 1 derivatives, and if we have x0 through xn are the roots of tn plus 1, and p is a polynomial that interpolates this function at these points, we can say that f of x minus p of x in absolute value is no bigger than 1 over 2n times n plus 1 factorial times the maximum of f the nth plus first derivative of f on the interval from -1 to 1. So we have a bound. Okay, if our function doesn't have derivatives that get too big, then we can really get a good approximation. In fact, this tells us if we make n big, then hey, we can get a really good approximation.